One of the jobs of a safety manager is to conduct risk assessments. Risk, as defined by safety professionals, is the function of the likelihood or probability of an incident and the consequences or the severity of that incident. Most of the time, safety managers do not have good access to quantitative probability data for calculating the actual probabilities. Most of the time, in most safety management, we are left guessing. Usually we come up with some pretty good guesses as to the likelihood or probability of an event occurring. But most of the time it's just a guess. But there are certain operations, certain complex systems where we may have access to good, reliable, valid probability data. When we have that good, reliable, valid probability data, then we can calculate the probabilities that an incident will occur. And we take that probability of an incident occurring combined with the consequences, the severity of consequences if it does occur, then we can come up with the best risk assessment. So what I want to talk about in this video is just the basic concept of probability. Then we'll talk about the addition rule. And as we move through this process, I'll give you some examples of some safety management situations where we might have good probability data and how we would use that probability data to help form our risk assessments. But first, let's talk about what we mean by probability. Simply speaking, probability is the chance of an outcome, the chance that something will happen. More technically, if you want more of a textbook definition, it's the ratio of number of observed events or occurrences to the number of possible events or occurrences. A coin flip is a good, simple example. That gets us in the arena of talking about probability. When you flip a coin, there's two possible outcomes, but only one's going to occur. So the ratio of observed events, and we're only going to observe one event, the ratio of that one observed event to the number of possible events, either a head or a tail, that's our probability. The probability of flipping a head is 1 to 2, or 1 over 2, or 50%. We could also look at another simple example, the roll of a six-sided die, a single die. There are 6 possible outcomes. So what is the probability of rolling a 3? It's going to be 1 out of 6. 3 is one possible outcome, is one event out of 6 possible outcomes. The ratio 1 to 6, 16.7%. This next one, I'm going to let you think about it for a second. I'm not going to give you too long or the video will take forever. But what is the probability of pulling an ace out of a deck of 52 cards? There are 4 aces. So what is the probability of pulling any of those 4 aces out of a deck of 52 cards? Okay. The ratio is 4 to 52, or 7.7%. There's a 7.7% chance that we're going to pull any ace out of a deck of 52 cards. Again, no jokers, just the actual cards without any additional cards added. 7.7%. If you go to casino, you get good at probability. Maybe you can count cards and you don't have to be a safety manager. But I wouldn't be too hopeful of that happening, though. Another thing we need to consider when we talk about probability is conditional probability. Conditional probability is when the probability of an occurrence is affected by previous events. You can talk about independent events, external events. We're talking about a situation with conditional probability where there are other events, external events that have occurred previously or at the same time that affect the probability, the likelihood of an outcome. Give you an example here. We'll use cards again. An ace is drawn from a deck of 52 cards. We've already established that the probability of drawing an ace out of a deck of 52 cards is 7.7%. What is the probability of drawing another ace on the next draw without replacing the first ace we selected? This is conditional probability. The probability on this second draw was affected by the first draw because we didn't put the card back in that we drew the first time. Conditional probability. So what is the probability of drawing an ace on the next draw without replacing the first ace we selected? It's going to be 3. There's only 3 aces left. 3 to 51. There's 3 aces and only 51 cards left because we didn't replace the original ace. So probability on the second draw is going to be 5.9%. What about an ace on the next draw? That's assuming that we did pull an ace on the second draw. On the third draw, now we're down to the third draw, we've already pulled 2 aces out of the deck. It's going to be 4%. 2 out of 50, 1 out of 25, or 4%. The probability of drawing a third ace out of the deck of 50. So that's an example of conditional probability. Let's talk about the probability addition rule. Sometimes we want to know the probability of one event or another event, 2 independent events. We want to know the probability of one or the other occurring. That's where the addition rule comes into play. Let's look at an example here. What is the probability of drawing the ace of spades or the ace of hearts from a deck of 52 cards? In this situation, one or the other event is what we're interested in. We add the probabilities for the occurrence of each event. Simply add the probabilities. This situation, we're first going to have to determine the probability of drawing a ace of spades. Then we're going to have to determine the probability of drawing the ace of hearts. And we're talking about one draw. One draw. What's the chance of an ace of spades or the ace of hearts? The probability of an ace of spades is 1 to 52.0192. Same thing for the probability of an ace of hearts. Once we have the probabilities, all we need to do is add them. In this situation, we would expect to draw either the ace of spades or the ace of hearts 384 times out of 10,000 possible occurrences, or 3.84% of the time. Now, I do want to mention this. This popped up there. I didn't say anything about it. That's a mathematical notation for what we're doing. What we got here, probability of x or y equals the probability of x plus the probability of y. Again, this would be the proper mathematical notation for what we're doing. But I don't want you all to get caught up in that. I want you to understand the concept. If you're looking at probability of one event or another, you take the probability of the one event, you take the probability of the other event, then you add them together. And that gives you the probability of one or the other. And you could have situations where there's 5 or 6 different events that you're looking at. It could be X or Y or Z. If you have 3 events that you're looking at, then you would add those 3 independent probabilities together to find the probability of X or Y or Z occurring. Let's look at another example. And this one's more from the safety management system safety side. We have a cooling system designed with 2 pumps. That's moving coolant through the system. If either pump fails, the system will overheat. Both pumps have to work for the system to work properly. If either one fails, the system will overheat. If the probability of failure for each pump is 0.00032, what is the probability of an overheating incident due to pump failure? Again, addition rule. Just like we had on the previous example. We're going to add those probabilities. And this is a little easier. It's given us the probabilities of failure for each pump. They're identical pumps, so the probability of failure for each pump is identical. Add those together. We would expect this to occur 64 times out of 100,000 possible occurrences, given these failure rates. And this is the kind of failure rate data or probability data that you can obtain from manufacturer specifications. Sometimes it's expressed as a probability of failure. Sometimes it's expressed as the mean time between failures, which we'll talk about in another video. But this kind of data, when we're talking about components of a system, this kind of data is available. Sometimes we may have to badger the manufacturer for the information, but this type of data is available. And if we're working with a complex system made up of components like these pumps, then we can calculate the probability of failure for that system. And I'm going to show you a really much more detailed example in one of our later videos. What we're doing here, we're leading up with these simple examples, we're leading up to what would be a more real-world type of scenario where we calculate the probability of failure in a system. Right, let's look at another example. A system may fail if either component X fails or component Y fails. If component X has a probability of failure of 0.5 and component Y has a probability of failure of 0.7, what is the system's overall probability of failure? It's an OR situation, so right out of the gate we're thinking it's going to be the addition rule. But the simple addition rule does not work because we're dealing with high probabilities of failure for each occurrence. If we simply add them together, we're going to end up with 1.2, meaning that our system is doomed to failure. There's a 120% chance that failure will occur. I mean, there's a high chance that failure will occur if you've got these kind of components, but it's not going to be 120%. There's a modified formula that needs to be used in situations like this when the failure rates of components are high. And this is the formula. The probability of failure for the system equals the probability of failure for X plus the probability of failure for Y minus the probability of failure for X multiplied by the probability of failure for Y. So when we plug these numbers in, 0.5 for the probability that X will fail, 0.7 for the probability that Y will fail, then we do the same inside the brackets, 0.5 and 0.7. Go ahead and multiply our terms inside the brackets. We end up with 0.35. We add the terms outside the brackets. We end up with 1.2. The probability of system failure is 0.85. 85% probability of failure. It's still a system that we need to work on to try to identify some components that have lower failure probabilities. Our system is not very safe or very reliable with these components. So look for different components. See, and that's another value in using good hard quantitative data. It allows us to see where we might be able to improve our system. Now, this formula that we're talking about here, which is really the technically correct formula to use in these situations. Even if we had lower probabilities of failure for our components, this is still the technically correct formula to use. but it's not necessary on the certification exams. And that leads me to another issue that I haven't mentioned. You will see this particular concept, these particular types of problems when you get ready to take the CSP exam here in 4 or 5 years. When you get to that point in your career, you're ready to take certification exams, which will mean a lot more money for you if you do get certified. This is what you're going to see. Probability is one of those core concepts that's covered on certification on the CSP exam, and you're going to run into problems like this. All right, well, that's it for the addition rule. We're just getting started with probability and how it can be used to determine the probability of failure of a system. But I'm going to go ahead and end this video here. In the next video, we'll take a look at the multiplication rule.